There is a speed at which your legs move that your prefrontal cortex cannot ignore. Not running, not jogging, not even brisk walking. Slower than that, somewhere around 2 miles per hour, roughly half the pace most people consider a normal walk, your brain enters a state that no amount of sitting, thinking, meditating, or sleeping can replicate. The neurons in your dorsolateral prefrontal cortex, the region responsible for working memory, planning, and abstract reasoning, begin firing in a pattern that researchers at Stanford and the University of Michigan have measured with functional MRI and portable EEG, a pattern that appears only during slow, quiet, self-paced locomotion and vanishes the moment you stop or the moment someone starts talking to you. This is not relaxation. Relaxation is a reduction in sympathetic nervous system activity. What happens during a slow, silent walk is something structurally different. It is a reorganization of neural resource allocation, a shift in which networks receive blood flow, which neurotransmitter systems dominate, and which oscillatory frequencies your cortex settles into. The result is a brain that solves problems it could not solve while sitting at a desk, retrieves memories it could not access while trying to remember, and generates connections between ideas that had no apparent relationship 5 minutes earlier. The mechanism is not mystical. It is biomechanical, neurochemical, and oscillatory, and it operates on principles that are as measurable as the voltage across a synapse. Let me tell you what is actually happening in your skull when you walk slowly and no one is talking. Your brain has 2 large-scale networks that operate in something close to mutual exclusion. The task-positive network, sometimes called the executive control network, activates when you are focused on an external problem, reading, calculating, following directions, having a conversation. The default mode network activates when you are not focused on anything external, when your mind wanders, when you daydream, when you stare out a window without seeing anything. These 2 networks are anti-correlated. When one is active, the other is suppressed. This is not a metaphor. It is a measurable hemodynamic relationship visible on fMRI. Blood flow increases in one network while simultaneously decreasing in the other. Here is the problem with modern life. For anyone over the age of about 40, you almost never let the default mode network run uninterrupted. Every moment of potential mind wandering is filled. The phone, the television, the radio in the car, the podcast during the walk, the audiobook before sleep, the news at breakfast. Your task-positive network is engaged almost continuously from waking to sleeping. The default mode network, which is where your brain consolidates memories, processes emotional experiences, simulates future scenarios, and makes creative associations between distant concepts, gets almost no uninterrupted runtime. Marcus Reichel at Washington University in St. Louis identified the default mode network in 2001 and spent the next 2 decades demonstrating that it is not idle brain activity. It is not your brain doing nothing. It is your brain doing something specific and essential that it cannot do while you are paying attention to external stimuli. The default mode network is where autobiographical memory is consolidated, where your sense of self is maintained, where social cognition operates, where you simulate the mental states of other people, and where creative insight emerges from the recombination of previously unrelated information. When you walk slowly in silence, something remarkable happens to the relationship between these 2 networks. Marilia Pezzo and Daniel Schwartz at Stanford published their findings in 2014, showing that walking increased creative output by an average of 60% compared to sitting. But the critical detail that most people missed in the coverage of that study was the condition. The effect was strongest during slow, self-paced walking without conversation or audio input. The moment you add a podcast, a phone call, a companion talking about their day, you re-engage the task-positive network and suppress the default mode network. The creative benefit collapses. It is not walking that improves thinking. It is walking in silence that improves thinking. The locomotion provides the physiological substrate. The silence provides the cognitive space. Both are required. Neither alone is sufficient. Now let me explain the physiology underneath this, because the mechanism is not simply that silence lets you think. Something is happening in your brainstem and your hippocampus that depends specifically on the rhythmic bilateral movement of slow walking, and it does not happen when you are sitting quietly in a dark room. Your hippocampus, the seahorse-shaped structure in your medial temporal lobe that is essential for memory formation and spatial navigation, generates a specific oscillatory rhythm called theta waves, electrical oscillations between 4 and 8 Hz. Hippocampal theta is associated with memory encoding, memory retrieval, spatial processing, and the binding of new information to existing knowledge structures. In rodents, hippocampal theta is generated almost exclusively during locomotion. The animal moves, theta appears. The animal stops, theta disappears. In humans, the relationship is more complex, but fundamentally similar. Ambulatory EEG studies, where subjects wear portable electroencephalography equipment while walking, show increased theta power in the hippocampal region during walking compared to standing or sitting. Here is where the speed matters. At very slow walking speeds, the kind where you are not trying to get anywhere, where your legs are moving at a pace that requires no cardiovascular effort and no navigational attention, your brain is free to allocate theta oscillations to memory processing rather than spatial navigation. At faster speeds, the hippocampus must dedicate more theta cycles to processing the spatial environment, tracking obstacles, maintaining balance, planning the route. At 2 miles per hour on a familiar path, the spatial demands are minimal. The theta rhythm is available for its other function, binding memories, making associations, retrieving stored information that your conscious mind has been unable to access. This is why you remember things during slow walks that you could not remember while sitting at your desk trying to remember them. The retrieval cue is not the environment, it is the oscillatory state. Your hippocampus, generating theta during slow locomotion, enters a retrieval mode that it cannot enter while you are sitting still and your theta power is low. The memory was always there. The access pathway required a specific neural oscillation that only locomotion reliably generates. There is a neurotransmitter dimension to this that makes the silence component non-negotiable. When you are processing language, whether listening to a podcast, having a conversation, or even reading signs as you walk through a city, your left hemisphere language networks are active and consuming a neurotransmitter called acetylcholine at high rates. Acetylcholine is also the primary neuromodulator of attention and memory encoding in the hippocampus. It cannot do both jobs simultaneously at full capacity. When your auditory cortex and Broca's area and Wernicke's area are processing incoming language, the cholinergic system is partially allocated to that task. Less acetylcholine is available for hippocampal memory operations. During silent walking, the cholinergic system is freed from language processing demands. The full supply of acetylcholine from the basal forebrain, specifically from the nucleus basalis of Meinert, is available to the hippocampus for memory consolidation and creative association. This is not a small effect. The cholinergic system is the single most important neuromodulatory input to the hippocampus for memory function. Its depletion is one of the primary mechanisms of cognitive decline in Alzheimer's disease. When you walk in silence, you are giving your hippocampus access to its full cholinergic supply. When you walk while listening to something, you are splitting that supply between language processing and memory operations. The brain that thinks better after a silent walk is a brain that had its primary memory neurotransmitter available at full concentration for the duration of the walk. There is another molecule involved, and this one explains why the effect is not just cognitive but emotional. Brain-derived neurotrophic factor, BDNF, is a protein that promotes the survival of existing neurons, encourages the growth of new neurons and synapses, and is essential for long-term memory formation. BDNF levels in the hippocampus increase with physical activity, even mild physical activity, even walking. Carl Kottmann at the University of California, Irvine, demonstrated across multiple studies that voluntary physical activity increases hippocampal BDNF expression in a dose-dependent manner, and that this increase correlates directly with improved performance on memory tasks. The critical finding for our purposes is that the BDNF increase does not require intense exercise. It requires movement. Sustained, rhythmic, voluntary movement. A slow walk of 20 to 40 minutes produces a measurable increase in circulating BDNF that peaks approximately 30 minutes after the walk ends and remains elevated for several hours. During this window, your hippocampus is in an enhanced state of plasticity. New synaptic connections form more easily. Memory traces consolidate more effectively. The associations your default mode network generated during the walk are more likely to be encoded into long-term storage. This is why the insight you had during the walk stays with you. It is not just that you thought of something interesting. It is that the neurochemical environment during and after the walk made that thought more likely to be consolidated into a durable memory. The BDNF created the conditions for the thought to stick. Without the walk, without the BDNF elevation, the same thought might have flickered through your default mode network and been lost, never encoded, never retrievable, never available for future use. Kirk Erickson at the University of Pittsburgh published a landmark study in 2011 showing that older adults who walked for 40 minutes 3 times per week for 1 year increased the volume of their hippocampus by approximately 2%. This reversed age-related hippocampal atrophy by 1 to 2 years. The control group, who did only stretching exercises, showed the expected age-related decline of approximately 1.4% over the same period. The walking group did not just slow the decline, they reversed it. Their hippocampi grew, in older adults. Through walking, not running, not high-intensity interval training. Walking. The hippocampus loses approximately 1 to 2% of its volume per year after age 55. This shrinkage correlates with declining memory performance and is one of the earliest structural changes visible in the progression toward dementia. Erickson showed that this trajectory is not fixed, it is modifiable. By walking, the mechanism is BDNF-mediated neurogenesis and synaptogenesis in the dentate gyrus, the subregion of the hippocampus where new neurons are born throughout life. Walking stimulates the birth of new neurons in the exact structure that aging is shrinking. The walk does not just help you think better today, it builds the physical substrate that will allow you to think at all in 10 years. Now, I need to tell you about what silence does to your brain independent of walking, because the two effects are synergistic and understanding both explains why the combination is so much more powerful than either alone. In 2013, Imke Kirste at Duke University was studying the effects of various auditory stimuli on neurogenesis in mice. She included a silence condition as a control, expecting it to show no effect. Instead, she found that 2 hours of silence per day produced significantly more new neurons in the hippocampus than any of the auditory conditions, including music, white noise, and pup calls. Silence was not a neutral baseline. It was an active stimulus for neurogenesis. The finding was unexpected and has been replicated in subsequent studies. The mechanism appears to involve the reduction of cortisol and norepinephrine that occurs during sustained silence, creating a neurochemical environment in the hippocampus that favors cell proliferation. Noise, even moderate background noise, activates the amygdala and triggers a low-level stress response. Not the acute fight or flight response, but a chronic elevation of baseline cortisol that most people living in modern environments experience continuously without recognizing it. The refrigerator hum, the traffic outside, the television in the next room, the heating system cycling, each of these produces a small amygdala activation and a small cortisol release, individually trivial, cumulatively significant. Cortisol at chronically elevated levels suppresses hippocampal neurogenesis, impairs memory consolidation, and reduces BDNF expression. The noise you have habituated to, the noise you no longer consciously notice, is still being processed by your amygdala and still elevating your baseline cortisol and still suppressing the neurogenesis that your hippocampus needs to maintain its volume and function. When you step outside into genuine silence, not the silence of a quiet room with a refrigerator and a clock and distant traffic, but the silence of a path where the only sounds are wind and birds and your own footsteps, your amygdala activity drops measurably. Cortisol production decreases. The hippocampal environment shifts from one that suppresses new cell growth to one that permits it. Combined with the BDNF elevation from walking, you have created the optimal neurochemical conditions for hippocampal neurogenesis. New neurons. born in the structure that makes your memories, stimulated by the combination of movement and silence that your great-grandparents experienced every single day without thinking about it. There is a rhythm to slow walking that synchronizes with your brain in a way that no other activity replicates. Your footsteps at a slow pace occur at approximately 1.5 to 2 Hz. This frequency falls within the delta to low theta range of neural oscillations. There is evidence from ambulatory EEG studies that the rhythmic sensory input from footfalls, the proprioceptive feedback from your joints, the vestibular input from your gentle lateral sway, entrains cortical oscillations toward the theta band. Your brain synchronizes its electrical activity to the rhythm of your steps. This is called sensorimotor entrainment, and it means that the act of walking slowly is not just permitting theta oscillations in your hippocampus, it is actively driving them. Your body is a metronome for your brain, and the tempo of a slow walk is the tempo your hippocampus needs for memory processing. This entrainment does not occur during fast walking or running because the step frequency is too high and the attentional demands of maintaining balance at speed recruit executive networks that suppress the default mode. It does not occur during sitting because there is no rhythmic sensorimotor input to drive the oscillation. It occurs specifically during slow, easy, undemanding locomotion, the kind where your body knows what to do and your mind is free to go wherever it wants. Let me tell you what happens to your prefrontal cortex during all of this, because the prefrontal cortex is where the thinking you notice actually occurs. Your dorsolateral prefrontal cortex handles working memory and logical reasoning. Your ventromedial prefrontal cortex handles value judgments and emotional regulation. Your anterior cingulate cortex monitors for conflicts and errors. During focused work, all three regions are heavily engaged, consuming glucose and oxygen at high rates, depleting local neurotransmitter supplies, and accumulating metabolic byproducts including adenosine, the molecule that makes you feel mentally fatigued. Adenosine accumulates in the prefrontal cortex during sustained cognitive effort. It binds to adenosine receptors on neurons and reduces their firing rate. This is the mechanism of mental fatigue. Not a metaphor, not a feeling. A molecule binding a receptor and reducing neural output. Coffee blocks adenosine receptors, which is why it temporarily restores alertness, but the adenosine is still there, still accumulating. The fatigue is deferred, not resolved. During a slow, silent walk, your prefrontal cortex is not engaged in demanding computation. The default mode network is running. The executive networks are quiet. Adenosine is being cleared by local blood flow, which increases during walking due to elevated cardiac output. The metabolic byproducts of sustained thinking are being washed away. Neurotransmitter supplies, dopamine, norepinephrine, acetylcholine, are being replenished. When you return from the walk and sit back down at your desk, your prefrontal cortex has been restored. Not rested in the way sleep rests it, but cleared of the specific metabolic debris that was impairing its function. The problem that seemed impossible before the walk now has an obvious solution. Not because the walk gave you the answer, because the walk removed the chemical obstruction that was preventing your prefrontal cortex from computing the answer it was always capable of computing. This is why the walk must be slow. At higher speeds, your prefrontal cortex is recruited for motor planning, obstacle avoidance, pace regulation, and route navigation. It does not get to rest. It switches from one demanding task to another. The adenosine continues accumulating. The restoration does not occur. A brisk walk for cardiovascular fitness is valuable for other reasons. But for cognitive restoration, for the specific clearing of prefrontal metabolic fatigue, the walk must be slow enough that your executive networks can fully disengage. And this is why the walk must be silent. Language processing, whether listening or speaking, is one of the most metabolically demanding operations your prefrontal cortex performs. Comprehending speech requires your dorsolateral prefrontal cortex to maintain the words in working memory, while your temporal lobe decodes their meaning. Producing speech requires your inferior frontal gyrus to select words, construct syntax, and coordinate articulation. Both operations consume the same neurotransmitter supplies and produce the same metabolic byproducts as any other demanding cognitive task. A walk with a podcast is not a rest for your prefrontal cortex. It is a different kind of work. The adenosine continues accumulating. The restoration does not occur. There is something else happening during silent walking that I have not yet mentioned, and it may be the most important mechanism of all for people over 60. Your brain has a waste clearance system called the glymphatic system, discovered by Maiken Nedergaard at the University of Rochester in 2012. During sleep, cerebrospinal fluid flows through channels surrounding blood vessels in the brain, flushing out metabolic waste products including amyloid beta, the protein that accumulates in Alzheimer's disease. The glymphatic system is most active during sleep, but recent research suggests it also operates at reduced capacity during quiet wakefulness, and that its efficiency is influenced by body position, cardiovascular activity, and autonomic nervous system state. During a slow walk in silence, your parasympathetic nervous system is more active than during focused mental work. Your heart rate is mildly elevated, increasing cerebral blood flow and the pressure gradients that drive glymphatic clearance. Your stress hormones are low, which favors the arterial pulsations that pump cerebrospinal fluid through the glymphatic channels. You are not sleeping, so the system is not running at full capacity. But you are in a physiological state that permits more waste clearance than sitting at a desk in a state of cognitive effort and mild stress. Every slow, silent walk is a partial cleaning cycle for your brain. Not as thorough as sleep, but supplementary to it. And for people whose sleep quality has declined with age, whose nighttime glymphatic clearance is already compromised, the daytime supplementation from quiet walking may be more important than anyone has yet quantified. Yoshifumi Miyazaki at Chiba University in Japan has spent decades studying what the Japanese call Shinrin-yoku, forest bathing, which in its simplest form is a slow, silent walk through a natural environment. His measurements show that 20 minutes of slow walking in a forest reduces salivary cortisol by 12 to 16%, reduces sympathetic nervous system activity as measured by heart rate variability, reduces blood pressure, and increases natural killer cell activity, a measure of immune function. The effects persist for days after a single session and accumulate with regular practice. The natural environment adds a dimension that a treadmill in a quiet room does not provide. Natural scenes engage what the environmental psychologists Rachel and Stephen Kaplan called soft fascination, a gentle, involuntary attention that occupies the sensory systems without demanding executive processing. The movement of leaves, the pattern of light through branches, the sound of water, these stimuli engage your brain just enough to prevent the restlessness that sometimes accompanies complete sensory deprivation, but not enough to activate the task-positive network. They hold you in the default mode sweet spot, the zone where your mind wanders productively rather than anxiously. This is different from walking on a busy street, where your executive networks must process traffic, navigate pedestrians, interpret signals, and maintain vigilance. Urban walking engages the task-positive network continuously. The cognitive restoration does not occur. The default mode network does not get its runtime. The theta oscillations are allocated to spatial navigation rather than memory processing. The environment matters, not because trees are magical, but because a natural path with minimal navigational demands and no social stimuli is the environment that allows your brain to enter the specific state where all of these mechanisms operate simultaneously. Let me connect this to something practical about aging and cognitive decline. The trajectory of cognitive aging is not fixed. It is not a predetermined decline that you watch helplessly. The research from Erickson, from Kottman, from Kirste, from Rachel, from every lab that has studied the intersection of movement, silence, and brain function converges on a single conclusion. The brain that is used in the way it evolved to be used, with daily periods of quiet locomotion through natural environments, maintains its structure and function far longer than the brain that is confined to chairs and bombarded with continuous stimulation. Your great-grandparents walked to the store. They walked to church. They walked to visit neighbors. They walked in the evening after dinner. They did not call it exercise. They did not call it meditation. They did not call it cognitive maintenance. They called it going for a walk. And during those walks, they were silent much of the time. Not because they had nothing to say, but because silence between familiar people was comfortable, and because the world was quieter, and because no one had yet invented a device that could fill every moment of silence with content. The loss of the daily silent walk from human life is not a minor lifestyle change. It is the removal of a primary maintenance input for the most complex structure in the known universe. Your brain evolved over millions of years in an environment where slow, quiet locomotion through natural settings was a daily occurrence. Every mechanism I have described, the theta entrainment, the default mode network runtime, the cholinergic availability, the BDNF elevation, the cortisol reduction, the adenosine clearance, the glymphatic supplementation, evolved to be activated by this specific behavior. The behavior that your species performed every single day for its entire evolutionary history until approximately 75 years ago. The chair is not neutral. The podcast is not neutral. The indoor environment is not neutral. Each of these is an active deprivation of an input your brain requires for maintenance. The cognitive decline that accompanies aging in modern sedentary populations is not entirely genetic. It is not entirely inevitable. It is partly the result of a brain that has been deprived of its primary maintenance behavior for decades. The silent walk is not a luxury. It is not a hobby. It is not something you do if you have time. It is maintenance. Like sleep. Like food. Like water. Your brain requires it to function at its capacity and to maintain its structure over time. If you are reading this and you are over 55, and your thinking feels slower than it used to, and your memory is less reliable than it was, and your sleep is fragmented, and your mood is flatter, and you spend most of your day sitting indoors with some form of audio or visual stimulation filling every quiet moment, then you are experiencing exactly what the neuroscience predicts for a brain deprived of its evolutionary maintenance input. The theta oscillations are not being generated. The default mode network is not getting its runtime. The cholinergic system is perpetually divided. The BDNF is not being elevated. The cortisol is not being cleared. The adenosine is accumulating. The hippocampus is shrinking at its expected rate rather than being maintained by the neurogenesis that movement and silence would provide. The prescription is not complicated. It is not expensive. It does not require equipment or instruction or a doctor's referral. 20 to 40 minutes, slow pace, no earbuds, no phone conversation, no companion who needs to talk. A path you know well enough that your executive networks can fully disengage. Ideally through trees or along water or across open ground where the visual environment provides soft fascination without demanding attention. Every day if possible. Most days at minimum. Your grandmother did not know about hippocampal theta oscillations or the default mode network or brain-derived neurotrophic factor or the glymphatic system. She did not need to. She knew that her husband thought more clearly after his evening walk. She knew that her own worries seemed smaller after a quiet turn around the garden. She knew that the neighbor who never left the house declined faster than the one who walked to the post office every morning. She knew that children who had been cooped up all day were irritable and scattered, and that sending them outside to walk it off actually worked. She knew all of this from observation, from a lifetime of watching what happened to people who moved quietly through the world and what happened to people who did not. Go for a walk, clear your head. That is what she said. She was describing prefrontal adenosine clearance and default mode network activation and hippocampal theta entrainment. She just called it clearing your head. And she was right. She was right about all of it. The neuroscience took 6 decades and billions of dollars in research funding to arrive at the same conclusion she reached by watching people live. Tomorrow morning, leave your phone on the table, step outside, walk slowly, listen to nothing but the air moving and your own footsteps on the ground. 20 minutes, no destination. No purpose except the walk itself. Your hippocampus will generate theta. Your default mode network will activate. Your prefrontal cortex will clear its metabolic debris. Your cholinergic system will flood your memory circuits with the neurotransmitter they need. BDNF will rise in the structure that makes you who you are. Cortisol will fall. New neurons will begin dividing in your dentate gyrus. And somewhere around minute 12, a thought will surface that you could not have produced sitting at your desk. A connection between two ideas that had no apparent relationship, a solution to a problem you had stopped consciously working on, a memory you had not accessed in years, arriving fully formed and vivid. That is not magic. That is your brain operating in the mode it was built for, the mode that silence and slow movement unlock, the mode that your grandmother knew about before anyone had ever imaged a living brain. The mode that is available to you tomorrow morning for the price of leaving your phone behind and walking out the door.